Hello everyone, my name is Itro and I would like to welcome you to another video. In this video, we are going to continue learning about clustering. In the previous video, we learned about hierarchical clustering and how we did hierarchical clustering in R. In this video, we're going to move away from hierarchical clusterings and start learning more about k-means clusterings. I know in the previous videos that we've discussed clusterings, I have already introduced you to k-means a little bit, but in this video our learning is going to become much deeper and we're going to understand different aspects of k-means clusterings. Alright, let's look at the slides. Okay, so after a few small recaps about clusterings and the concepts that we've already learned, we're going to discuss k-means, and we're going to learn k-means and add depth to our understanding of k-means by using a toy example. And then we are going to discuss how do we set k in k-means. This is a very important conversation, and it's actually the most important part of being able to apply k-means appropriately. And then we'll discuss the weakness and the strength of k-means, and then I will offer some summary. Alright, so we do remember when we go about the task of clustering, it is known as unsupervised because we don't have any dependent attributes. So when we don't have a dependent attribute, all we have are a set of attributes that we want to find the emergent pattern from the data. And clustering, the way it goes about this emergent pattern is by looking at all of these attributes and trying to find groups of data objects that are similar to one another at the same time they are different than the rest of the data objects. So that's how clustering is. We've seen hierarchical clustering in the previous video. In this video, we're going to talk about k-means. K-means is perhaps the most well-known clustering algorithm. Clustering and k-means for some people go in hand. And a lot of times when you want clusterings and in the industry clusterings are used, k-means are being used. And of course in those methods that we talked about, we've got hierarchical, partitioning, grid-based. K-means the partitioning method. And also something that you need to know about k-means, it's a random method. So every time you run it, you might have a different result. But k-means has proven to show that the results that is created by random, they are showing meaningful similarity when the results are coming out. And of course, it's also known as centroid-based clustering, something that we will understand what it means when we get to the depth of k-means. So this is the simple flow chart of k-means that we've already seen, but basically k-means works in a very simple loop. So this is a very, very simple loop that k-means work, and no wonder why k-means is very popular. It's very simple, but at the same time, it's very effective. Using a toy example, we want to learn about k-means more. But before that, let us have a small conversation about what we mean by centroid. This is something that we've taken for granted, that we already know and understand what centroid is. But centroid is a specific terminology that we use when we talk about clusterings. So centroid is basically a representation of each cluster, each group of the data object. And it can be calculated in many different ways. Two of the most frequent ways of calculating the centroid is, the first one is just calculating the mean of all of the data objects in the cluster. And this is perhaps the one that is the most accurate centroid for the cluster, because each data object has the equal weight in saying what should be the centroid, right? What is the centroid of that cluster? Another way is to move away from having that equality between all of the data objects and moving towards making sure that the representative of each cluster is actually a data object. And that is when we go for midweight. And midweight is basically a data object within the cluster that has the smallest distance from the other data objects in the same cluster. So, if you use mean, your algorithm is k-means. If you use memdoid for your centroid, your algorithm is going to be k-memdoid. So, in this specific video, we're going to learn about k-means, but k-memdoid just simply is, a little bit computationally more expensive, but in certain situations, it can become more appropriate to apply. But anyway, we are going to use k-means, and that it means the centroid's definition we're using here is the mean of all of the data objects in the cluster. So now let's talk about our toy dataset. So we've got the toy dataset. We've got D1 and D2 here. This is dimension 1 and dimension 2, and we want to cluster these data objects using k-means of k equal to 2. So when we visualize our data, this is what we get, right? So this is the x-axis or dimension 1, and this is the y-axis and dimension 2. So that's how you get from this data set to this representation. So this is the same data set, but it's being represented visually here, right? So what is the first step for k-means? Of course, we do know that k is equal to, and after that, we need to do is to randomly select k data objects from the dataset as centroid of the k clusters, right? And that means for this situation, we need to randomly select 2 data objects. We start off as them being the centroid of the clusters, right? So let's say these 2 are chosen, number 9 and number 11. And when we do that now, because we've got the centroid, we have to figure out which data object is going to be part of which cluster. So by a simple calculation of distance, for example 7 to 9 and 7 to 11, we will realize that 7 should be a part of the data objects that 9 is the centroid for, right? So we do that for all of them. It's very simple visually, but computationally wise, you have to actually calculate all of these distances. But visually it's very simple. But we will realize that these are cluster that 9 is the centroid to, and then these are cluster 11 that cluster that 11 is the centroid to. So now that we know all of our data objects within each cluster, the next step is going to be updating the centroid, right? In the beginning, we did this randomly. Each of these 2 data objects were just started off as centroid, but now that we do know the data objects of each cluster, we can actually update the centroid. What was the centroid? The centroid is the mean of all of the data objects in each cluster. So once you calculate the mean, these are going to be the centroid for cluster orange, and this is going to be the centroid for cluster green. Now, once the centroid is updated, we have to check if, because we changed the centroid, is any data object, are there any data objects that because of this change of centroid would change their membership in the data, right? So now you start seeing the simplicity and the effectiveness of k-means algorithm. So you have to check the distance of all of the data objects from all of the centroids. And if there is a change in your membership of one of the data objects, this keeps continuing. So here, once you check, you will see that for data object 18, even though we started off as data object 18 being a part of green cluster, but once the centroids are updated, we can see that data object 18 is actually closer to a cluster centroid of cluster orange. So because of that, this membership changes, right? Pay attention that this becomes orange. So now because this became orange, now what do? We have to update the centroid, because now one cluster is gaining an additional data object and the other cluster is losing a data object. So once you actually do this, what's going to happen? The centroid of the cluster that is gaining a data object is going to move a little bit towards the data object, right? Because it's going to gravitate the centroids towards itself, this new data object, right? So this will move a little bit closer to 18, you see, and the other one, this one, moves a little bit further from 18, right? Did you see? And I'm gonna, let the animation runs again. So this moves closer to it, and the center of the green cluster, because it has lost this data object, it moves away from it. Pay attention. All right, so now we do the same thing again. We check all of the data objects from the different centroids, and we see if there is, a change. There is a change possible. And when we do that, in this case, we do see that there is no reassigning possible. Therefore, this becomes our final result. You see, k-means is as simple as this. And if you were paying close attention, you can see the simplicity and effectiveness of this algorithm. This is a genius algorithm. It's simple, but it's effective. So now that we were able to sort of see the simplicity of k-means and move on the flow chart to understand k-means, let us add a little bit more depth to our understanding, because here what we did, we just looked at things visually, and what k-means actually is doing is going to do everything computationally. So all of these distances that we sort of took for granted, that we would for example know that of course 3 is closer to this centroid than this centroid. We took for granted that we could just eyeball. Computer cannot do that. There is no eyeballing with the computers. The computer have to actually can calculate all of the distances. So to add a little bit of depth to our understanding, let us look at how all of these calculations would have looked like in Excel, right? So this is the same data, but it's a different representation. And we chose these two data objects as our arbitrary centroids in the beginning, right? So once we do that, now we have to calculate the distance from each of these data objects from centroid 1 and centroid 2. Pay attention, centroid 1 is 9, the same data object as 9, and centroid 2 is the same data object as 11, right? So we calculate all of these distances. You can see that these are all calculations. Now we have to figure out which one is closer to which centroid. So we go through all of these, and we say, for example, this is smaller than this one, therefore this is cluster 2, so on and so forth. Do you see now there are a lot of calculations that k-means have to go through? And then once we have all of our data objects, so you pay attention here, we've got a cluster now, right? So we update our centroid, and the centroids are the average of all of the data objects within each group, right? So now our centroids are updated. Now we do check, you see these are centroid 1 and centroid 2. Now we do check the distance from these new centroids, right? So these new centroids are plugged in here, and now we calculate the distances, and we do see that for data object 18, it used to be, let's go back, it used to be data object 18. It used to be, C2 was smaller, 0.41 against 0.47, but after the centroid were updated, we've got 0.47 to 0.48, right? So this is definitely a changing data object, as we saw in the visual parts of going about clustering, k-means clustering. So we update the centroids, and then we check again if it is possible to change any of the data objects, and the answer is no, and that tells us that the clusters are fine. So now we have a sort of a depth of understanding of k-means from two perspectives. We do completely understand the procedures, the simple procedure. At the same time, we do understand if a computer wants to go about this k-means, there are going to be computation, and that computation is important. And one thing that we need to remember about k-means is that k-means is random and is not optimal, right? So there is no guarantee that when k-means is run, you've got the optimal clusters. I mean, what we mean by that is if there are clusters in the data object that the distance from the data object to their centroid is the minimum it can be for a specific k. It is possible that k-means on some run comes to this optimal solution, but it's not guaranteed. So one of the advices you have to always carry with you when you're using k-means, it's the fact that it's always good to run k-means a few times and sort of like see if it's reaching a similar output or similar result, which means that k-means is onto something. And at the same time, perhaps you could argue if k-means more often reaches to the same conclusion, and because of that we might consider that as a better outcome, which is again, it's not an optimal way to go about this, but this perhaps bring us closer to optimality. So pay attention, you want to run k-means a few times. All right, let's talk a little bit about the computational complexity and why k-means is scalable. I mean, when you run k-means in a computer, there are going to be a nested loop with 3 levels, right? You're going to have a loop on your data objects, number of data objects. Every time you do the calculations, you have to do for all of your data objects. And there is going to be another nested loop. You've got to do everything for the number of k's you have. And for all of these k and n, every time you reassign, there is an iteration, it's going to be another loop, right? So the computation complexity is n multiply k multiply t. So, this may sound that, it's not as scalable as we're discussing, but if you have worked with k-means, and this is something that's been researched, t, which is the number of iteration we need for k-means to get into stable clusters, so there is no reassigning, is always smaller than the number of data objects. It's way smaller in the most cases. I mean, in this example we had 20 data objects. The number of times we need to iterate was 2. And we've seen that this is always smaller. At the same time, we're doing clusterings, and n is always significantly, k is always significantly smaller than n, right? We might want to do 1 million of data objects into 2 clusters, 3 clusters, 10 clusters. I mean, we don't want to go more than a number that is going to be overwhelming for our understanding, right? So k is also always significantly smaller than n. Therefore, the computational complexity of k-means barely reaches n2, which is a scalable level. So that's why k-means is a very computationally robust method, a computationally scalable and robust sustainable method. All right, so the next conversation we're going to have is how do we go about setting k's? I mean, we're going to discuss, we're going to see that the major weakness of k-means is the fact that we don't know the number of clusters, and k-means does not do any help for us to tell us how many clusters are possible in the data objects, in the data sets. So we are the one who have to decide this, and this can be a challenging task for us, because how do we know the number of clusters, right? So there are a few approaches you can go about setting k, and we're going to discuss all of these right now. So one of them is expert opinion, meaning that if you have a data set from a specific area, someone who has been making decision in that area and have known that area, they may have some ideas of what is the number of clusters, or what are the different number of groups that are in that population. So that could be an approach. I mean, you just ask that expert opinion. That expert could be you, because you've been working there and you know that environment. So that's a legit approach if you actually indeed have meaningful insight to that environment. Then the second approach is going by how many clusters you need, right? There are analytic cases that you just need a specific cluster because you want to do something with those data objects. For instance, let's say you have a marketing campaign and you want to assign 5 different segments of your marketing based on the types of customer to 5 different marketing associates that you want them to focus on a specific customers, right? So you've got these 5 people, you just want to assign these customers to them, right? So you use k as 5, right? As simple as that, and because you need your data objects to be meaningfully grouped into a specific number of groups. So that's another approach that sometimes happens. Then another one is to just start off with a rule of thumb, the square root of n divided by 2. And when you do that, you would expect to get the square root of 2n as your each cluster having this amount of data objects. This is just a rule of thumb. If you have no idea, you might want to start from that. A second approach, another approach is going about visualizing your whole dataset using some method that can reduce the dimension of your data meaningfully. For example, we could use PCA. Do you remember principal component analysis? Its main impact on the data, it would transform the data so the first few PCs would have the most amount of variation, quote unquote, information of across all of the population. So for example, here we've got from the same data set that we've been clustering in the past couple of videos, we've got PC1, PC2, and PC3, right? So by looking at this visual, we might talk ourselves into I see sort of a cluster here, so another cluster here, so 2, another cluster here, 3, I see a cluster here, 4, I see an outlier here, 6, and I see another cluster, 7. So we talk ourselves into saying we've got 7 clusters by just having done this. So we are not sort of like putting K completely blindly. We have done some visualization, but we do see that there is some meaningful clusters when we visualize the data set using these methods. Another method you could have used to visualize without having to lose any information, here we must have lost some information because we're only using PC1 to PC3, is self-organizing map, which is another great dimension reduction methodology for visualization, which is something we don't discuss in this course or in my videos, at least for now. But it's a great tool. I mean, you wanna if this is a very important decision. What is K? You might want to look into that. What is the most frequent and most popular way to go about this is using elbow method. Elbow method is when you experiment with different possible Ks. Let's say you can have K as 2, 3, 4, 5, right? And calculating a goodness of clustering metric, right? And these metrics are, a few of them are out there. One of them is sum of squared error, which means what is the summation of all of the errors. Meaning that when you cluster a group of data objects into a cluster, you basically are losing some information, right? So you're re-representing your data objects by one column. So you're losing some information. And that loss of information can be calculated by, calculating the distance of every data object to their centroid in the cluster that they belong to, and summing all of those up, right? And if this SSE is a value when you have 2 clusters, you can be sure that SSE drops when you have 3 clusters, right? Because now you have more clusters. It always expected, because you've got more clusters, there is more opportunity for these clusters to represent the data in a better way, right? So you always expect this to decrease, but if there is an elbow which is showing that the rate of decrease has significantly dropped, right? The rate of decrease from 2 to 3 was very large, but the rate of decrease from 3 to 4 was not as large as the rate of decrease from 2 to 3. This may indicate that perhaps there is something about this 3, KS3, that can basically help us say, okay, we've got probably 3 clusters, right? So this is called elbow method. The rationale is written here. I mean, if adding a data object, a cluster, always adding a cluster will help this specific metric, like SSE. Therefore, should we have added another one if the rate of improvement decreased so significantly? So basically, this is the rationale, but before moving on from this, I would like to mention that this rationale does not work on all of the metrics for cluster, right? One of the metrics that we will learn is silhouette. Silhouette score is a great metric for clustering analysis. We do sort of see this sort of line plot of the progression of this metric. Also, it's good to see that, but you don't expect to see this effect there. I mean, if you use SSE, sum of square error, this is where you see that effect. So you want to use this with SSE, basically. Alright, so lastly, before we get into summary, we're going to discuss the weakness and the strength of the algorithm. So the weakness, there are two weaknesses for this algorithm. One is k-means only find circular clusters. I mean, all of the partitioning method has this weakness that they cannot find randomly shaped clusters. And that's an okay thing, because most of the time, because our data objects have, linear relationship with one another, most of the data objects have linear relationship with one another, most of the attributes, then k-means that we have nothing to worry about it, because it's only find circular clusters. If there is a case that our attributes do not form linear relationship with one another, then we might want to stay away from k-means, because it only can find circular clusters. Another thing that we already discussed is that we are the one who's in charge of finding how many clusters we need, and k-means does not help in that arena to us. I mean, we did say that we could use k-means to find by doing some experimental calculations like this, but at the same time it does not inherently provide that. The strength of k-means, of course, is very well known, simple, and well regarded algorithm, and it's very scalable. These are the two strengths that certainly in many cases trump the weaknesses. Alright, so in this video we talked about k-means, and we got a deeper understanding and deeper appreciation for this algorithm using a toy example, toy data set, and then we talked about k-means scalability. We also talked about how we would go about setting k, and in the end we also discussed a little bit about the weakness and the strength of k-means. Until the next video.